We're going to look here at number 3. We see 4 terms here and 4 terms here, so we want to try to factor everything. Once we factor everything, most of these things are easy to see once we get it factored. We still have to do a little bit of work on some things. But to factor these 4 terms, we're going to try grouping for both of these, and if that doesn't work, we have to do P's and Q's, but as it turns out for this problem, that's going to work for both of them. So for the numerator, we're going to group these two and group these two. We're going to factor out x squared, and then we're going to factor out negative 9. Make sure that when you pull that negative, both of these terms in here become positive. So now, out of these two terms, we're going to pull out the x plus 2. And then this factors, there's one more step there that it factors with. This x squared minus 9 is a difference of squares. And so this is what the numerator is going to be. To factor the denominator, we're also going to do grouping. And over here, we're going to pull out a negative 4. Be careful that this sign is also negative. When you pull out a negative from a positive, you get a negative left. You can think about distributing it back. Negative times a negative would give you positive 20 there. Out of these two terms, I'm now going to GCF the x minus 5. And then again, I see a difference of squares. And so I get this as my denominator. So if I put these two now back together, this line and this line, if I put them now back together as numerator and denominator, I have x plus 2, x plus 3, x minus 3 over x minus 5, x plus 2, x minus 2. So this is the factored form of the function that I started with. So now we can go through and we can start to answer some of these questions. Let's answer part A. Let's find the horizontal asymptotes. I'm going to record these answers right here. So the horizontal asymptote is based on, we didn't actually have to factor to see that. We could have seen it before we factored. That is based on the dominant term of each of my numerator and denominator, and then also on their coefficients. So since this power is equal to this power, since m is equal to n, we just take the leading coefficients, and that gives me my horizontal asymptote. Horizontal asymptotes go this way, so this is a y equals equation. So this horizontal asymptote is y equals 1 over 1, or just y equals 1. When we look for holes, we want to actually look at this factored form and see if anything cancels. What we see is that we have one term here that cancels, so that means that the x-coordinate of the hole is at negative 2. That also means I can simplify what I have here. So my simplified form of this initial function is this. So for the rest of this problem, we're actually going to use this simplified form. So if the hole happens at negative 2, when x is negative 2, and we want to know what the y value is, well, we just plug negative 2 in for x. So we can kind of do this a little bit in our head. If we plug negative 2 into this first set of parentheses here, negative 2 plus 3 is 1. Negative 2 minus 3 is negative 5. Negative 2 minus 5 is negative 7. And negative 2 minus 2 is negative 4. And so this gives me negative 5 over positive 28. This is the y value when I plugged a negative 2 in. So this is the y value of the hole. And so when I graph that, I'm actually going to kind of just estimate it. Okay, to find the vertical asymptotes, remember that vertical asymptotes are vertical lines that the graph is never going to cross. So that happens when we have a domain restriction. If you look in the denominator right here of this simplified form, you can see that we're going to have two vertical asymptotes. There's one here at x equals 5, and then there's another one at x equals 2. And again, these are vertical lines that this graph is never going to cross. And that we see that by looking for those domain restrictions down there. Part D says, does the graph cross the horizontal asymptotes? We're going back to the horizontal asymptote where y equals 1, and we want to see if this simplified expression, or this simplified equation, crosses at 1. So I want to see if this touches this when I set them equal to each other. So I'm going to actually set them equal to each other here. So I'm going to say 1 equals this simplified version of my function. Well, to solve this, I'm going to take both of these, I'm going to multiply by x minus 5, x minus 2 on both sides. So they cancel out over here, and so you just have this over here. So now we need to actually expand both of these. This gives me x squared minus 7x plus 10, and this gives me x squared minus 9, because again these are conjugate pairs. You can subtract x squared from both sides and they both go away. So now we have just a simple equation to solve. Negative 7x equals negative 19. So x equals 19 over 7. So it does cross, and it crosses when x equals 19 over 7, and the y value where it crosses has to be this 1, because it's crossing this line where y is 1, and so it doesn't matter where it's crossing it at x, it has to be, that y value has to be this y value right here, so it has to be 1. So we don't actually have to plug that back in here, thank goodness, but if we did plug it back in here, we would get out that y equals 1. But we also know that from what it's doing as it's crossing. Okay, part E says to find the y-intercept. Again, that's something easiest done from standard form, because the y-intercept is found by plugging in 0 for x. Now, of course, you could do that here, and you would get negative 9 over positive 10. Or you can just plug in 0 here, 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 so those all go away. Plug in 0 here, 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 those all go away. So essentially, this is your y-intercept, which is negative 18 over 20, or negative 9 over 10. Which again is the same thing you would have gotten if you plugged in 0 here. 3 times negative 3, negative 5 times negative 2, you would have gotten negative 9 over 10. So that's the y-intercept. And then the last thing we need to find are the x-intercepts. Well, x-intercepts happen when y is 0. So you're basically putting a 0 here, and the first thing you're going to do is multiply both sides by this denominator. But this whole side is going to stay 0 because it's already a 0. You multiply by anything you want, it's still going to be 0. So essentially, my x-intercepts are just when these two factors are equal to 0. So you can see we have an x-intercept at negative 3 and an x-intercept at positive 3. Okay, so we have found all the pieces. All we're going to do now is put all these pieces on the graph and then sort of draw the shape that's left. So these pieces are going to basically indicate most of what the graph is going to look like. So we have a horizontal asymptote at 1, the dotted line at 1. We have a hole at negative 2. Now, negative 5/28, it's about negative 1/5. It's about negative 5/25, which is about negative 1/5. So it's kind of just barely below the x-axis. So negative 2, we're just going to put it about right there. There's your hole. Vertical asymptotes at 2, 3, 4, 5, and x equals 5. We are going to cross this horizontal asymptote at 19/7 1. So we know we're crossing it. It's got to be the y value has to be 1. 7 goes into 19 2 whole times. That would give us 14. And then 5/7 more. So it actually almost goes in 3 times. So we're crossing it at 1, 2. We're kind of crossing it about right here. Just short of 3. We're going to be crossing it. Now that's a solid circle because that's an actual point on the graph. This is a hole, so that one needs to be an open circle. The y-intercept is almost negative 1, so the y-intercept is about right there. And then we have x-intercepts at negative 3 and positive 3. 1, 2, 3. Okay? And so we can now basically graph. It's pretty easy to see what's going to happen right here. Right? We know that these graphs are going to approach these asymptotes basically straight away. So this graph is going to go like this. There's a hole there, and then it's going to come down, and now it's going to start approaching this asymptote here. These vertical asymptotes just have a multiplicity of 1, and so the graph is going to, if it's approaching this vertical asymptote on the left side, if it's going to negative infinity, and this has a multiplicity of 1 here, then the other part of the graph is going to, from the right side, it's going to approach from positive infinity. So if this side's going down, this side is going to start way up here, the next side. And this graph is going to fall, it's going to hug that asymptote till it gets here. It's going to cross the horizontal asymptote, and then you can see it's going to switch sides. It's going to go to the other asymptote here. Okay, we don't actually have any piece of information for this graph over here, so we don't know if it's going to be down here or up here. except for the fact that this asymptote again has a multiplicity of 1. So on the left side, if it's approaching the negative infinity side, that means on the right side it needs to be coming from positive infinity. So this one's actually going to start up here, and it's going to curve around to the other. It's going to just hug those asymptotes. And we didn't see any of these points from the graph because we didn't have an x-intercept or a y-intercept or nothing particularly interesting happened over there. But we know that the graph is going to look like that because of the asymptotes.